Welcome to lesson 23 on power system analysis. In this lesson, we will review the topics that we had discussed earlier on power system component modeling. We will start first with the transformer model, then we will talk about the synchronous machine model, and finally we will review the load models. So, since this lesson is basically a review, we will go through the whole thing at a faster pace because you have already gone through this details of this earlier. So, we will start with the transformer model. As we have said earlier, we have in a system different voltage levels. The generator generates at an optimal voltage level, which is somewhere around 11 to 25 kV. So, generator voltage can be anywhere in between that. For transmission, since we are transmitting large amount of power over large distances, we need to transmit it over very high voltages, and therefore, we need transformers to step up this voltage from the level of 11 to 25 kV to a much higher voltage of the order of 132 kV or 220 kV or 400 kV, depending on the amount of power to be transmitted and the distance over which it has to be transmitted. So, we need a transformer at this point where we connect the generator to the transmission system. These transformers are called generator transformers, and many times these transformers are coupled with each unit of the generator. So, they are also many times called as unit transformers. So, each generator has its own transformer. So, they form one unit of generator and transformer. After transmission, when we have brought the power to the load centers, there we have to distribute it to various loads, and that is done at lower voltage levels, which we call the sub-transmission voltage level. So, these voltage levels can be 66 kV, 33 kV and so on. So, we need again a transformer to step down the voltage from the transmission level to sub-transmission level, and so we use these transformers, step down transformers, here at the substation to step down the voltage to maybe 33 kV. After that, again it is stepped down to lower voltages for distribution to smaller consumers. It can be brought down to 11 kV and then further brought down from 11 kV to 400 volt or 415 volt to be precise, and there this 415 volt 3-phase power is transmitted, and then you get it at your home here at 230 volt single phase when you get connected to a line and the neutral of a 415 volt 3-phase system. So, this is how the power network works, and as we see at each stage we need the transformers. So, we have to model these transformers mathematically when we are trying to analyze the transmission system. So, we will now go into the modeling of the transformers. So, before we start with the mathematical model, we must understand that there are two kinds of transformers that we use. This depends on the basic construction principles. One type is called the shell type transformer, where the core, as you see here, this is made up of iron stampings, and the windings, there are two windings, the primary winding or this winding where current I1 is flowing, and there is a secondary winding where current I2 is flowing. These two windings are put on the central limb, that is, the winding is surrounded by the core. This kind of a transformer is called a shell type transformer. We can have a simpler arrangement like this, where the winding are on the outer limbs. There are only two limbs of this transformer, and the windings are on the outer limb, and this type of a transformer where the winding is surrounding the core or enclosed is called the core type of transformer. Basically, as far as the working of the transformer is concerned, for our purpose we will find their working to be very similar. There are certain differences, but we will not go into those aspects in this course. So, what we find is the transformers consist of an iron core for providing the path to the magnetic flux, and we have two windings which are linked by the same flux. So, there is a mutual coupling between the two windings by this flux, and because of this mutual flux, which is time varying, we get the voltage. If we energize one side and we get some current flowing into this, then a flux is set up like this, and since this flux is time varying and it is cutting this winding also, therefore, you are going to get a voltage induced here. Now, if you connect a load here, you will get a current flowing through this. Now, when a current starts flowing through this, then a magnetic field is set up by this current, which is going to oppose this flux here, and because of this, what happens is the flux in the core will reduce, try to reduce. If the flux here reduces, the voltage here cannot be maintained, since this voltage is an applied voltage, which is a fixed voltage. So, what happens? More current will flow through this to maintain this voltage and thereby maintaining this flux. So, whenever we connect a load here and the current starts flowing, we get a reflected current to start flowing from this side also to balance the flux which is trying to oppose the flux in the core. So, basically the operation of transformer you will find is of that of a constant flux. Constant means it is a time varying flux, but the constant in magnitude as far as it is the phasor is concerned, and that is this flux is maintained at the same level in this core, whatever may be the load on this side. So, if you increase the load, this will try to increase the current here, and that will try to reduce the flux here, but more current will flow here to try and maintain this flux in the core. So, this is how the transformer works, and before we start doing mathematical model for this transformer, we will get into the concept of ideal transformer. That is, we are considering a transformer which is ideal in the sense that its job is to transform the voltage levels and the currents on the two sides. Now, this transformer we assume has infinite core permeability, that is, the permeability of the core is infinite. What does this really mean? It means that there is no MMF required to create the magnetic flux in the core. That is, there is no current which is exciting current required to create the flux. All flux is confined in the core. That is, it again says that the core, since it has infinite permeability, all the flux will try to reside inside the core. It will not go out where the permeability is lower, and so the reluctance to the flux path is going to be higher. Another assumption or another property of the ideal transformer is that the transformer winding has 0 resistance. It simply means there is no power loss which takes place in this transformer, and there is also no voltage drop which takes place in this transformer. The another assumption that we make for an ideal transformer is that there is no core loss, that is, there is no hysteresis or eddy current losses which take place in the core. Of course, we know these assumptions are not really valid. A physical transformer will have a finite permeability, it has a winding resistance, and it also has the core losses associated with it. But the concept of an ideal transformer provides us a very elegant concept for modeling the transformer. So, what we find for an ideal transformer? The input power is equal to the output power. What we have as the input power, the instantaneous value of input power, that is P1, is equal to V1 into I1. Now, these small case letters are meant for instantaneous values. So, the instantaneous power at the input end is Vi into Ii, and similarly P2 is equal to V2 into I2. Now, since we have assumed for this transformer there is no loss, so P1 is equal to P2 or V1 I1 is equal to V2 I2. If we are talking in terms of the phasors instead of instantaneous values of currents and voltages, then we can write that V I conjugate V1 I1 conjugate is the complex power, input power is equal to V2 I2 conjugate, that is the complex output power. That is, we say S1 is equal to S2, where S1 is the complex input power, which is equal to P1 plus JQ1, and S2 is equal to P2 plus JQ2, where P1 is the input real power, Q1 is the reactive power from the input side, and P2 is the output real power and Q2 is the output reactive power. Now, in case of a physical transformer, what we have finite permeability, there are core losses, there is loss in winding because winding has a resistance, and there is going to be voltage drop because again the core does not have a finite infinite permeability. So, some flux will pass through the air path, that is, if you see this transformer, here we are seeing that all the flux is going through the core, but we will find that some flux may be following this path on this side like this, here it will be like this, and similarly here it will be like this. That is, some of the flux is not going to link the other winding. This kind of flux we call as the leakage flux. So, there is going to be some leakage flux, because of which the flux which is created by this, all the flux that is created by the current flowing here does not link this, and therefore, the voltage generated here is not going to be exactly in the same proportion. That is, there is going to be some loss in the voltage, and this is occurring because of the leakage flux. So, we in a physical transformer all these things happen, that is, permeability is finite, core loss is there, winding loss is there, and leakage flux is there. Now, how do we incorporate this into the ideal transformer model? So, we have an ideal transformer model here, which basically means that it is doing only the current and voltage transformation. There are no losses, no current required, and all that, whatever is the concept that we have talked about for ideal transformer. So, we want to now take out that infinite permeability assumption. That is, we are saying that the transformer has finite permeability. What does it mean? It means that some current will be required to set up the flux in the transformer core. This can be modeled as an inductance which is in parallel with the ideal transformer. That is, an inductance here will draw a current I m. This current is going to be lagging this voltage by 90 degree, which is going to be the case for the flux which is going to be set up as we know. So, we can model the effect of finite permeability by means of this inductance x m here. So, here what we have V 1 is the voltage, I 1 is the current. Here we have a current, a part of the current is going through this. So, this current is somewhat less. This current is I 2 dash, where I 2 is the current here, which is equal to I 2 by A, and I 2 by A plus I 1 m, which is the current flowing in this inductance to take care of the finite permeability. If we add these two phasors, then we will get the phasor current here. Similarly, if we want to take care of the core losses, which consist of hysteresis and eddy current losses, we can model it by simply using a resistance or a conductance in parallel with this inductance. Here, since these two are forming parallel branches, therefore, it is much easier to work with susceptance and conductance. Therefore, we are writing this instead of R C, the resistance, we are writing this as conductance to take care of the core losses, this as B m, the susceptance to take care of the current for finite permeability. So, the core losses and finite permeability can be taken care of by this kind of a circuit, where this current I 1 m is the total current which is flowing through this parallel path, which denotes the core losses and the finite permeability part of the system. Now, why have we put this as a parallel branch? The reason behind this is very simple. As soon as we excite the transformer, there is going to be a current which will flow through the transformer to set up the flux, and as soon as this time varying flux is set up in the core, we are going to have a hysteresis and eddy current loss in the core, and this is not dependent on the load. As soon as we excite the transformer, this is going to happen. So, this is going to be there even at no load. So, this is dependent on the voltage that we use to excite this transformer, so or energize this transformer. Therefore, we have put this as a parallel branch. So, this parallel branch across this ideal transformer takes care of these two parts. Now, the resistance and the leakage flux part can be taken care of by means of resistance of the winding here and the reactance to take care of the leakage flux part. So, this gives the impedance of the winding, where R S 1 is the resistance of the side 1, that is the primary side, and X S 1 is the leakage flux part, which is represented by a leakage reactance X S 1. So, this is what we get. Similarly, on the other side also we have a winding. So, it has resistance and leakage reactance. So, that is given by R S 2 and X S 2. So, this is a model for the transformer. Now, as we know, just like voltage and currents are transformed, we had seen we can transform the impedances from one side to the other side, and therefore, if we do that, then this side impedance, which is here, can be transformed and put on this side, then we get it like this. Now, once we have a model like this, what we are finding, we have resistance and leakage reactance, we have the core which is having core losses, and the leakage and the excitation current for building up the flux. Then we have the winding resistance and the leakage reactance for the secondary winding. So, this is the model that we have. Now, here again we can make an assumption that the current in this is basically reactive, in the sense that this is going to be almost 90 degrees with respect to the voltage, because this is much smaller, this is much larger. So, this is going to be like this, and since if we have loaded this transformer, the power factor of load will be around 0.8, 0.9. So, the current here is going to be almost in phase with the voltage with a small angle here. So, the phasor sum, if we take, is going to be almost similar to this, that is, this I 1 is going to be almost equal to I 2 dash, and therefore, the error in assuming I 1 is equal to I 2 dash is not going to be very large, and if we make that assumption, then we can combine this like this. So, we have shifted this on, that is, if you see here, we have shifted this here, and then we have combined these two resistance and reactances which come in series, and therefore, we have got finally a simplified model like this for the transformer, and this is the mathematical model or the circuit model for a practical transformer. Now, in this case, as we see, the series impedance ZS is going to be like this, RS plus JXS, and the shunt admittance is GC minus JBN. So, here we have the admittance part as GC, which is 1 by Rm plus 1 by JXM, that is basically 1 by GC, this is GC minus JBN. Now, here RS is equal to RS1 plus A square RS2, that is the transform resistance from the secondary side to the primary side. XS is equal to XS1 plus A square XS2, that is the transform reactance taking care of the leakage reactance part of the secondary winding. Now, in practical transformers, RS is very small compared to Rm, XS is very small compared to XM, and XS is much larger than RS. In many cases, what we do is, many cases this current is generally very small, and also this current is at 90 degrees almost in quadrature with this current. So, this is many times neglected, and the final model of the transformer can be used as just a series impedance in series with the ideal transformer. Now, most of the transformers, since we are using 3-phase system, are 3-phase transformers. 3-phase transformers can be built as on a single core as a 3-phase transformer, or we can build 3-phase transformers by using a bank of 3 single-phase transformers. These transformers, or the 3-phase windings of these transformers, both on primary and the secondary side, can be connected either as a star or as a delta. Like here we have shown, this is connected as a star, and this is also connected as a star. So, we have a star-star transformer. This is a bank of 3 single phase transformer, one transformer here, another transformer here, and the other one here, and we have connected them as star star transformer, which on a circuit will look like this. Similarly, we can have transformers as star and delta connection. Many times we use this type of connection. Now, if you look at this circuit, then you find that the phase A and the phase A here, if you see, they have a phasor displacement of 30 degrees. This is what we get. That is, when we have a star delta transformer, then the delta side voltage is leading in this case by 30 degrees. We can have a inverse also, that is, it can lag by 30 degrees as well if we make connection in that way. So, star delta transformers, when we have, we find that the voltage and current on the two sides have a phasor displacement of 30 degrees, and we can take care of this in our mathematical model by using the same model that we have for a transformer. That is, we have the shunt part taking care of the core losses and the magnetizing current, and the series impedance taking care of the leakage reactance and the resistance of the winding. This is the ideal transformer, and we have added a phase shifter of 30 degrees, because if we have a star delta transformer, this will be a plus 30 degrees if the connection is done as shown here. So, if we have this connection, then this will be a plus 30 degree. If we have the reverse connection, then we will have this as minus 30 degree. So, this is how we model the 3-phase transformers. Next, we will talk about the model for synchronous machine. Now, synchronous machine have a fixed relationship between the speed and the frequency, and this relationship is given by the frequency f is equal to p by 2 into n by 60, where n is the speed in RPM for the rotor and p is the number of poles of the synchronous machine. This we can write also as p by 2 into Fm, where Fm is the mechanical frequency. That is, you can see it in terms of number of rotations per second. Now, this is a very interesting relationship, because it gives you a relationship between electrical frequency and the mechanical frequency. That is, if we are using a 2-pole machine, then this P is equal to 2. So, F is equal to Fm. If we are using a 4-pole machine, then F is equal to 4 by 2, that is 2 into Fm. So, the electrical frequency is going to be twice that of mechanical frequency. Similarly, if we are going to use 6-pole or 8-pole machine, the electrical frequency is going to be higher than the mechanical frequency. Now, again, for synchronous machines also, we have normally two kinds of machines based on the type of the rotor of the machine. One model that we use is shown here, where we have the rotor, which is a round cylindrical structure on which the winding is placed. This kind of machine are called round rotor machines, and these are generally used for large turbo alternators, which are run by steam turbines. Because these run at very high speed, a cylindrical rotor structure is much more convenient as well as stable for the system, because the centrifugal forces at that high speed are going to be very high, and they can be, these windings can be braced for those high centrifugal forces on a round rotor machine. Whereas the other kind of machine, we call them as salient pole machine. As you see here, the rotors are protruded from the center, they are coming out like this. So, this machine, the poles are salient, they are protruded coming out, and these machines therefore are called salient pole machines. Now, generally these machines are low speed machines. Now, for hydel generation, where the speed of the hydro turbine is very much dependent on the head, in fact the optimum speed is based on what is the height of the water above the turbine, that is the head, and therefore these machines run at much lower speed. Since the frequency of the system is same, that is, we in India we use 50 hertz as the frequency. Therefore, if suppose the speed is only 300 rpm, then for keeping the frequency 50, how many poles will be required? If we go back to this equation, we find that the speed is 300 rpm. This is, so this is 300 by 60, so this is 5, and this is 50. So, here we need how many poles? 20 poles will be required for this machine. So, depending on the speed, the number of poles change, and for low speed machines we need very large number of poles, and therefore, there we use salient pole structure. Now, first we will talk about the steady state model for mathematical model for the synchronous machine. Now, in steady state, if we see these synchronous machine, the voltage, since all the three phases are symmetrical, we talk only of one phase. The other two phases, that is phase A, if we talk about phase B, is going to lag phase A by 120 degree, and phase C is going to lag phase B by 120 degree. So, voltage and currents of phase A is and B and C are symmetrical, except that they will be 120 degree out of phase from each other. So, here if we see, if the voltage generated by the synchronous machine in phase A, or say the terminal voltage is given by this root 2 times V A cos omega t, and E A dash, that is the internal voltage generated by the machine, is E A dash is root 2 into E I cos omega t plus delta, we will see what this is, and I A is equal to root 2 I A cos omega t minus theta, where theta is the power factor angle, or the angle by which the current is lagging the voltage. So, with this in phasors, if we want to write, we will write V A is equal to V A angle 0 degree, E A dash is equal to E I angle delta, and I A is equal to I A angle minus theta, where what is V A? The terminal voltage. Terminal voltage is going to be equal to the generated voltage minus what? The drop, voltage drop due to current flowing through the armature winding resistance. So, due to armature resistance, the voltage drop R I A minus again the drop due to the self reactance of the rotor winding. Since the winding is wound as a coil, so it has a reactance. So, self reactance or self inductance L S. So, it is j omega L S into I A, this is the drop due to armature self reactance, and since there is mutual reactances associated because of the currents flowing in the other phases. With those windings also they have the mutual flux between them. Therefore, there is a mutual inductance MS, and for the stator windings, therefore, we have drop due to armature mutual reactance as j omega MS into IA. Therefore, we can write the total impedance as ZD is equal to R plus JXD, which is equal to R plus j omega LS plus MS, LS plus MS. Okay. So, this is what we get, and the circuit model for the synchronous machine can be put like this, where this for the machine acting as a generator, we have VA is equal to EA or EI minus R I into R plus j omega LS plus MS, that is EI minus IA into ZD, which is equal to EI minus IARA minus JXD into IA. If it is acting as a motor, then we are exciting from here. Therefore, VA is equal to EI plus this, that is EI is equal to VA minus this. So, VA is equal to EI plus IA ZD, that is equal to EI plus IAR plus J IA XD. So, this is a very simple model for the synchronous machine, which when acting as a generator or acting as a motor. This is a model which is used for steady state operation of the synchronous machine. Now, synchronous machine, as we know, has excitation control, and therefore, we can control the reactive power also. That is, excitation control can control the generated voltage, and therefore, it can also control the reactive power output of the machine. Now, here we see the complex power S is equal to P plus JQ, which that is the complex. If we are talking about a synchronous generator, this will be the power output from the synchronous generator will be equal to the terminal voltage into IA conjugate. We are talking of a single phase. Since if we are talking of 3-phase machines, then we will have to multiply the power by 3, or here VT is the phase voltage, not the line voltage. So, VT into IA conjugate, which we are writing as VT into IA cos theta plus j sin theta. Since we have taken the conjugate, we are writing this. So, P is equal to VT into IA cos theta, that is the real part, and Q is equal to VT into IA sin theta, that is the imaginary part. This j term is coming. So, that is the imaginary part. So, the reactive power is this part. Now, what is IA? IA is equal to E angle delta minus VT divided by JXD, that is the reactance. And if we take the conjugate of IA, then it is EI minus delta, the conjugate we are taking, minus VT, since its angle is taken as 0. So, there is no conjugate for that, and minus j x t. So, now if we substitute that is V t into I a conjugate, then we are going to get this relationship, and if we substitute for all this delta angle here, then we get finally P is equal to V t into E I by x t into sin delta, and Q is equal to V t by x t into E I cos delta minus V t. Now, these are very important relationships. It tells us that the real power output of the synchronous machine depends on the power angle delta, that is the angle by which the internal voltage or the generated voltage of the machine leads the terminal voltage. If this angle delta is negative, that means the machine will be acting as a motor, because P will be negative in that case. We also see from this relationship that Q is dependent on Vt or EI. So, what we are finding is that P is predominantly related with the power angle and not so much with the voltage. Of course, there is voltage relationship, but this dependence on sin delta is much more, because normally voltage is kept constant or very near to the rated value. But Q, if we want to change the reactive power output of the machine, then we have to change the excitation. By changing this EI, we can control the reactive power output of the machine very much. Now, what is the how much we can load the machine? A synchronous machine can be loaded up to what extent? This we can find out by looking at what are the limits which come into play. First is MVA loading limit. The maximum MVA cannot exceed the generator rating. Why? It simply depends on the maximum current that can be allowed, because if we allow more current than the rated value, the heating is going to be much more than the cooling which is provided, and therefore the temperature will keep rising and the machine may burn out. Therefore, this MVA loading limit is based on the current or the heating limit which is permissible by the design. Then the other one limit is megawatt loading limit, that is the real power loading limit, how much real power we can get out of the machine. The maximum megawatt cannot exceed the rated power limit. Why it cannot do that? Because it is being driven by a turbine, and turbine has a rated capacity. You can't get more output from that. Therefore, that gives us the limit of the real power that we can take out from the machine. Maximum field current limit. Again, we cannot excite the machine beyond a certain value, because the rotor current is going to exceed and rotor heating is going to go up. Therefore, the maximum current that can be allowed in the rotor limits the reactive power supply also. Stability limit, this is basically a dynamic aspect, that is generally we cannot allow this machine to work beyond a delta angle of 90 degrees. If you see here, if we have the maximum power that we can get out from the machine is when delta is 90 degrees. In fact, for practical purposes, we cannot work this machine more than normally around 15 to 20 or maximum 30 degrees. This is imposed because if we have sudden outages or faults on the system, the machines need to absorb this sudden large changes or jerks on the system, and the transient stability of the system may be threatened if we work at larger delta angles. That is, if we go very near to delta is equal to 90 degree, then even small changes may bring oscillations which can make system become unstable. So, this is the capability curve that we get for the generator. This is the delta max that we fix, maybe 30 degrees, 35 degrees, whatever it is. This is the curve for the P max. This is the curve for the MVA limit, and this is for the field current limits. So, it has to work within this region, where this part is P, that is, this is P on the y axis and Q on the x axis. So, this is a very important curve, and we have to see that our operating point at all times is within this region. If it goes beyond this region, then we have violated the operating constraints of the machine. Now, all this that we talked about, steady state model, all this is, even for dynamics, is to some extent valid for round rotor machines. But in case of salient pole machines, if you see here, the air gap in the pole region and between the interpole region is very much different, and therefore, the reluctance of the paths are different, and therefore, the inductances are going to be very different, and therefore, we cannot use a uniform model for this. We have to, in this case, use a 2-axis model, that is, one axis which is the direct axis along the pole face, and another axis which is in quadrature with it along the interpolar region. So, this is, if you see, an angle of 90 degree electrical. The angle here and here between north and south is 180 degree electrical. So, this is 90 degree electrical. So, we use a 2-axis model for the case of salient pole machines. I will not go into the details because we have already done this earlier. So, we can write down the equations for this machine for the flux linkage of phase A, phase B and phase C in terms of the self and mutual inductances and the currents flowing in the different windings, that is, the stator windings A, B and C, and the field winding, this current IF. Now, one of the major problems, as we have seen, because the flux paths are not same in the polar and interpolar region, what we have is all these inductances are dependent on the angle theta, and since they are dependent on angle theta, this angle theta keeps changing with the rotation, and therefore, all these inductances are time varying inductances. So, if we see these values, I had already told you earlier when we talked about the synchronous machine model. So, all the mutual inductances, self inductances, rotor inductances, rotor mutual inductances, stator rotor mutual inductances, all these we find that most of these inductances are time varying inductances, mainly because the flux path is not same in the polar and interpolar region, and therefore, analysis of this kind of a machine becomes very complex. In order to make this simpler, what we do is we use a transformation called Parkes transformation. The idea of this transformation is to transform the stationary 3-phase winding of the stator into 2 windings basically, or 3 windings, one which is in phase with the rotor, other which is in quadrature with the rotor, and the third one which is along the axis of the rotor. Since that has nothing much to do, so we generally do not use that part, but we have D axis which we call the direct axis, which is in the phase with the rotor, a quadrature axis which is at 90 degrees to the rotor, and the third one a 0 axis. So, DQ0 frame of reference. We transform the ABC phase reference values into DQ0 frame of reference by using this path transformation. And this dq0 frame of reference, since it is along with the rotor, it rotates at the same speed as that of the rotor. So, what we do, this transformation, that is for the current dq0 can be got by multiplying this transformation matrix with the phasor values. Same thing for the voltage, dq0 can be obtained by P multiplied by voltage, and same thing for the flux. We can do that. If we use this transformation, then we can write all these equations for inductances and the flux linkages, and we find that in this case most of the inductances have become constant, because now the dq0 frame is also rotating along with the rotor. So, these time varying inductances are no longer there. So, this is about this, as I said, there is the rotor, the direct axis and the quadrature axis, and this keeps rotating at the same speed along with the rotor. So, we do that, then we will write all the relations for voltage and the flux linkages in terms of dq0 frame of reference, and we avoid the time varying inductances in this case. So, this is what we get. If we do this, we have got this direct axis circuit where we have this is the field circuit, resistance and the inductance of the field, and this has a coupling with the direct axis because the two are in the same axis. So, here we have KMF as the coupling factor, LD is the direct axis inductance, R is the resistance of the stator winding, and omega lambda q is the speed voltage generated because of the q axis flux, because the voltage is normally generated at 90 degrees to the flux. So, this relationship is there. So, q axis flux generates the direct axis voltage. Similarly, we have the circuit for the q axis where the voltage generated is speed voltage omega lambda q, LQ is the direct quadrature axis inductance, and R is the winding resistance. And we find that these two circuits are, that is the q axis circuit is not coupled to any circuit, it is independent. So, the path transformation provides what? A direct axis circuit which rotates with the field circuit and is mutually coupled to it. A quadrature axis circuit which is displaced 90 degree from the d axis and thus has no mutual inductance with the field or other d axis circuit, although it rotates in synchronism with them. And a stationary standalone 0 coil with no coupling to any other circuit and thus is not shown, it is not used as such. For transient conditions, the same thing happens, except that we have the damper winding coming into play, and using this circuit we can use the transient and subtransient effect. What happens is that this damper circuit, whenever there is oscillation in the machine, this damper circuit comes into play, and since its time constant is very small, this dies off very quickly, and therefore, this circuit becomes open. There is no current flowing through this, and these two circuits are only valid, and then this field time constant somewhat larger. So, that again dies out with some time, and then finally, we have only the synchronous impedance of the circuit remaining, and therefore, we define 3 different reactances or impedances for this circuit. One is in which all the 3 circuits are there, since these three will be in parallel. Therefore, the total inductance is much lower, and this is what is happening in the initial part, and this we call as the subtransient reactance. When the damper part dies out, then we have only these two inductances which will be in parallel, and therefore, this we call as the transient reactance or the direct axis transient reactance. And finally, when this current dies out, then we have only this circuit which is the steady state or the synchronous reactance of the machine. So, we normally have three different kinds of reactances associated with it. In quadrature axis, we have the damper winding and we have the Q axis coil. We do not have any field winding coupling. Therefore, in this case we have a subtransient reactance when field winding the damper winding and the quadrature axis winding are present. When the damper current dies out, we have only the Q axis current flowing. So, we have a subtransient and a steady state or quadrature axis reactance, synchronous reactance of the machine. So, we have XQ and XQ double dash which we use for the subtransient part. XQ dash is generally not there. So, XQ dash normally people take same as XQ, whereas in case of the direct axis we have XD double dash which is much smaller than XD dash and which is smaller than XD as such. In the quadrature axis we have two windings, the damper winding and the Q axis winding on the stator. Now, when the fault occurs, initial current will flow in the damper winding as well as in this quadrature axis winding which are coupled, and since R will be much larger than L, this current decays very fast. So, initially we see the subtransient condition, and after this current decays out we get only the XQ part. So, we have in quadrature axis the subtransient reactance and then we have the quadrature axis reactance. Next, we will take up the load modeling. Loads have voltage and frequency dependence, and because of this change in voltage and frequency in the system, the value of these loads change and therefore, they affect the behavior of the system. We have a large number and different types of load which differ considerably in characteristics, and most of the time what we do is at any particular bus we aggregate these different types of load into a single load model. So, the different types of load that we have are lighting loads, heating load, induction motor loads and synchronous motor loads. We have already discussed about the characteristics of these, like lighting load has real power is independent of frequency and voltage to 1.5 to the power 1.5. Reactive power is very small. Similarly, for heating loads it is independent of frequency and real power is dependent on V square, and it can be represented as a constant resistance. We have induction machine loads which have also PV and QV characteristics as well as PF and QF characteristics. We will not go into details of this. This is just showing a family of curves for variation of voltage for P and Q, and similarly for synchronous machine the Q varies like this whereas P varies like this. And there are other categories in which we can categorize the loads are residential load, industrial and commercial load. This is done for aggregation of the loads, like we add up various loads into one aggregated load. So, we can composite loads can be modeled as constant MVA load, constant impedance load, constant current type loads and voltage and frequency sensitive loads. All these types of load can be aggregated as a complex model.